Hello, reInvent. I hope you're having fun, and I hope you've got all your steps in today, because if you haven't, you can probably get them in tomorrow. Definitely the fun is going to continue this evening, and I know it's a late session, so thanks very much for attending. In this session, I'm very pleased to have with me one of our customers, Creative Assembly, a game studio from the UK, and they're going to talk about how they deliver games at scale with AWS. Before we get started, I'll introduce myself. My name is Mark Easton. I'm a solution architect at AWS, and that means that my role is to work with games customers and help them on their technical journeys as they move and run things on AWS. And I'm going to be joined by Seb Maynard, who's the technical director of live services at Creative Assembly, and he's lucky enough to work on some really massively popular games. So to start with, I'm going to provide a little context about the video games industry. I'll touch on some of the challenges of building technology for games, and I'll talk through a little bit of some of the common things that we see customers doing on AWS. I'm then going to hand over to Seb. He's going to tell you about Creative Assembly's first cloud steps, how they evolved on their journey to reach high levels of scale. So if you're into games, you'll get a peek behind the curtains today of what it takes to build a highly successful game. If you're not so much into games, you'll get a warts and all story about how AWS can be used to scale for complex requirements. So the video games industry is all about delivering a great player experience, which means game developers need infrastructure and solutions that are going to support their game vision. The success of new games is often unpredictable. So that means elasticity is really important to ensure that game infrastructure can scale based on an uncertain number of players. So game developers need servers or services that can scale to potentially millions of players, and they need services, supporting services that will scale up as well, so databases that might reach terabytes or petabytes of data. Contemporary games players, though, they're a challenging lot. They all expect their games to have regular and compelling updates, and that means game developers need faster time to market and really highly efficient workflows to ensure they can build games and update games to keep the player's attention. So one of the things I love about games customers is they're all so different from each other. From one-person indie studios to AAA studios with thousands of employees, every one of them has their own unique way of doing things. However, while they're all different, there's some common themes that we see them wanting to use the cloud for. Firstly, when building games, well, pretty much like any developer, they have the standard requirements of build pipelines, version control, all those things that are required to build software. But they've also got unique requirements for the video games industry, such as working with complex asset workflows for videos, images, audio, things like baking light maps, which can be compute intensive and be highly elastic. When it comes to running games, one of the very key workloads that we see customers using is game servers. So most multiplayer games run on dedicated servers, and those need to be running globally because there's players all across the globe wanting low latency, sort of fast games. And also, game servers need to be highly elastic because they need to scale up and scale down as the players come and go. Finally, video games industry is a hit-based industry. So growing the player base is really vital for a game's success. But growing successful games is complicated. An essential part of running a game is running live ops and analytics services to keep the game running and to grow engagement with players. So hopefully that's given you a brief overview of how our games customers use AWS. But without further ado, I'd like to introduce you to Seb Maynard, who's going to tell you how Creative Assembly have used AWS to grow some of the biggest games around. Seb.
Thank you, Mark. Hello, everyone. I'm Seb. I'm the technical director for the live services team. Ta-da. at Creative Assembly. We are a games company, like Mark mentioned. We've been building games for quite a long time, 35 years, 36, actually, it might be this year, in the countryside, in between London and the beach. Yeah, there's not a lot else going on in the countryside other than us. We've made 42 games so far. We started absolutely ages ago making games in DOS with EA Sports. We moved on to making Total War games in the early 2000s. We've made a couple of games in the Alien universe and Halo universe. We've had some mobile games along the way. And we've just announced Hyenas, which is a first-person shooter in space. That's in alpha at the moment. The main goal of the company is to deliver rich, connected experiences to our millions of players. We have millions of players in all the countries, hundreds of thousands of people playing our games at any point, with thousands of requests a second. So my team, the live services team, we build the platforms and services and features that make that possible, basically, and we do the whole thing on AWS. When I joined the company 11 years ago, that is roughly how the infrastructure looked. There were a couple of additional bits here and there. I think there was an SQS queue involved somewhere. But yeah, I mean, it was a load balancer, EC2 Classic, VPCs weren't a thing, and it was kind of, okay, we want an online game, we want a connected experience, we need some infrastructure, go. Make an online game brings with it a whole load of new challenges that are very different than making AAA Total War titles. The games that we had, they have millions of players. They're published on Steam. They're published on Epic, Microsoft Store now. We had some console games as well. But none of them had this sort of online component, this persistent online universe that sort of keeps track of your player progression, your player state between game sessions, between machines that you happen to be on. We basically needed to build a platform. We needed to replicate some of the stuff that Steam did, but in a way that wouldn't be dependent on Steam. So we could use it on other things. We could use it on games that weren't in places where Steam wasn't available. We didn't really know what the game was going to be yet. We didn't really have any infrastructure people. We didn't have any sysadmins who would want to maintain this whole thing. And I'd spent 5 years previously at a different games company building billing systems and payment processing and credit card integration stuff. And all of that comes with basically the money processing thing is offline, get out of bed and fix it. And I never, ever, ever wanted to do that ever again. So goal number one when building a platform for a new thing that we didn't know what it was yet was, I don't care what it does, but it's not going to wake me up. What we needed was some services to support an evolving game. We didn't know what the game was going to be. We knew that it was going to be somehow based around Total War. We knew that it was going to be a free-to-play, probably, maybe not free-to-play. We didn't really know. If it was free-to-play, it would have microtransactions, and it would have very deep meta. It would have in-game transactions for buying cosmetics or using soft currency to unlock more stuff in a tech tree. If it wasn't going to be free-to-play, it would have different kinds of purchasing and different kinds of monetization models. But it would still be a rich Total War model, right? The experiences you get in Total War are non-trivial. They are the opposite of a casual game. And we needed to be able to build some services and tech that could deal with that. At the same time, the game designers were evolving all the time. They were coming up with new ideas of what they could put into the game, new ideas of what they should put into the game, what the market's doing at the moment, what players seem to be interested in using. We were experimenting with different server tech. We were looking at different platform providers. People like Amazon were starting to pop up. And whilst we were building the set of services, we didn't want to be baking in game functionality, baking in, this is the stuff that the game can do. That didn't really belong in the game client. We wanted it to be configurable on the service. It needed to be something that the game designers could change at any point. They could change the pricing, they could change the balance, they could change the items that were available, they could change the relationship between the different items. So one day we might have a Total War unit who's got a sword, and that's it. That's the model. You go into battle, you've got lots of people with swords. And then the next day we've got a unit, and that's hundreds of people with swords. And some of them have got arrows. Some of them are actually on horseback. And the next day, we'd have a commander, and he's got loads of units, and each of those units has loads of men, and they've all got different ammo, and different weapons, and different armor. Maybe they've got some cosmetics. They're like different hats. You can't have that hat on this unit. That doesn't make sense. Obviously, you can't put a sword on a horse. You can't put a horse on a person, right? There's rules. There's sort of a structure to the whole thing, but that structure's changing all the time. So how do you build a service that can deal with this, potentially for different games at the same time? So we kind of split it up into these three things. You've got services, which is all the online stuff that I was building with my team. You had the game client, which was all the Total War engine stuff, the stuff people could see, the things they could interact with. And then you had the game data. And game data seems like a nice sort of, it's a blob. It's not a blob. It's basically the idea of all the configuration for all the different aspects of a game. So pricing, balance, meta, matchmaking rules, matchmaking balance rules, the structure and validation rules of how these things on an individual user's profile can fit together. If we put all of that knowledge as a state into the game data thing, and we make the game service pull all of that state when it fires up, and we make the game client pull all of that state when it fires up, we can update the game client separately, as long as the game data structure doesn't change too much, and as long as the services are backwards compatible. We can update the other two whenever we want, and the game client doesn't need to change. We can update the game client whenever we want, and the other two don't need to change. Similarly, we can update the game data, push out new pricing, new items, new availability of whatever we want, and we don't have to redeploy any of the services, or, critically, take the game offline for the players. So that was kind of where we were. Again, didn't really know what the game was, but we were starting to get a feel for the complexity that was going to be involved in this thing. This is roughly how the infrastructure looked a year or so into building this new game. After a long time of prototyping, we settled on AWS. It did all the things that managing a data center in London with sysadmins did, and we didn't have to do any of it. It also had some really nice things for helping you sleep more, like fixing machines when they die, or spinning in a new machine when something gets taken out, or hard drives that will tell you when they've failed and be replaced with another one automatically, and we don't have to get involved. We spent quite a long time trying to decide what tech we should use on these machines, right? It was a games company. We had lots and lots of C++ programmers, lots of people who've spent years and years building extremely optimized, extremely clever, very densely packed binaries of C++ wizardry, which is great, unless you're building something that's changing all the time. And you don't really know how this thing's going to work, and it needs to be bulletproof in production. Otherwise, you're going to get woken up. So we settled on Erlang. It's a system platform framework thing by Ericsson from the sort of late 80s. It's a bit like Prolog mixed with a bit of Haskell with something like Akka, which is a actor model thing for Java. It's this very strange way of writing software, but it means that you can isolate the blast radius, basically, of anything that goes wrong. It's going to be constrained to a very, very isolated piece of tech. So we started modeling all of our users. They were an individual process. They'd be in a single server somewhere. And if that user process dies, that's fine. It will get recreated, and no one else will know. And that, again, helps us get towards our goal of don't wake me up. Pair that with graphs, right? You can see Graphite running on there. We read a bunch of blog posts around that time of Etsy. They had just started talking about their infrastructure, how they were doing things, and they had a blog post that summarized was roughly, if it moves, graph it, and if it doesn't move, graph it until it does move. And we thought, this is great. This is going to help us find where we're going to get woken up and maybe how we can program around it so that we don't. So we graphed everything. Every event that came into the service, every event that the matchmaking did, the profile did, they all got graphed somehow. And then we started thinking about, should we have triggers? Should we have alerts on these graphs at different things? Or should we actually have alerts on when the graph changes shape? It doesn't matter what the value is, as long as the slope of the graph hasn't changed too much. Add into that S3, which was this just wonder tech at the time. I think nowadays we just kind of take it for granted. But 11, 12 years ago, the idea that you could just say, hey, internet, save my file, and then anyone in the world could download that file, and they'd get the right version of it. building a game service that can pull in all of the configuration that defines how that game thing is going to run, from a magic wonder service that lets you push out new versions whenever you want, and everyone in the world can then get the new one. This was great, so we made heavy use of it. Pair that with DynamoDB. It took us a while to get to DynamoDB. We went via SimpleDB, which was, again, wonder tech, but had its own quirks. DynamoDB took a while to get to the point where we could use it in the way we wanted, but once it did, it was brilliant, and now we use it for basically everything. We've got these relay servers, so EC2 instances running very small C++ binaries that just do packet shuffling between player on one side of the world, player on another side of the world. Ideally, those two players are on the same side of the world, and they've got a relay server really close to them, otherwise your latency is going to be horrendous. So we fired up relay servers all over the place in lots of different Amazon regions. And then for the regions that Amazon didn't cover, we fired up these relay servers in dedicated server hosting in places like Russia and Siberia. And again, we graphed them with graphite. So we've got loads of graphite, got loads of EC2, lots of Erlang all over the place, loads of regions, using Route 53 for all of the DNS, do everything by host names, which meant that all of our services were individually addressable by host name. We didn't have to do any service discovery, any service anything. It was just the name of the service dot some domain, and it worked. Pair that with IAM, Identity and Access Management, and basically we had a pretty resilient way of building a service without having to do any of the hard work. However, we were building a game that we didn't know how big it was going to be. We didn't know how popular it was going to be. We knew that, in theory, all the Total War people in the world would want it, and that's millions of them, or none of them. We don't know which. So we need to make sure that our matchmaking handles that. We need to make sure that our systems aren't so brittly scaled that when we've got no users online, we're just setting fire to money. So we had to sort of build that in. Alongside that, we sort of had this epiphany that there's way more to scale than just the number of servers you've got, or the number of database connections you can handle, or how fast your dynamos are configured. You've got the traditional scale stuff that people talk about. How much data, how much bandwidth, how many API requests are you getting a second? How many servers are you going to need to deal with all that stuff? That's fine. I think by this point, 2014, 2015, that was pretty well understood. On the other side, you've got all this stuff that people didn't talk about. This was their secret sauce. And it was the stuff that actually we were trying to bake in right from the beginning, accidentally, by setting a goal of just don't wake me up. It kind of enforced all of this other stuff. Automated operations, right? We want everything to react without us having to kick it. We want quality from the beginning. So shift-left testing for all of your automation. You want to make sure that your unit tests, your common tests, your integration tests, your end-to-end tests, they all happen without you having to tell them to happen. And if they go wrong, they stop stuff. Like, you don't want people having to get involved to stop a delivery that's bad. And you don't want to have people to get involved to let a delivery happen that's good. Delivery, right? That's basically everything from write code to it's in the player's hands. It needs to be streamlined, and it needs to scale with the number of things you have in your service and the number of people you have in your team. Your team needs to get bigger, and the way you manage that team also needs to scale. The way you do stuff with 3 devs, building a thing to solve a problem, and the way you handle a team with 50 people in it, with 4 parallel product teams, who are all completely empowered, and we've got product managers and different SDETs and SREs in different places, and shared code, running stuff for lots of different games at the same time. Obviously, wildly different. And unless you've got some concept that that's going to be where you are, you need to be thinking about it from the beginning. If you cobble together what you've sort of built, and then at the very end think, oh, how are we going to run this? It's going to be dead in the water. So all of that, we decided we're going to make a platform. It's not just going to be a bunch of tech for a couple of games. It's going to be a thing. It's going to be something that we can give to a game team. They can embed it. They can embed some interface layer to it, an SDK ideally, or at least a bunch of APIs that are well documented. And they can pick and choose which of the services they want to use. They can work with us to understand how the bloody hell to configure the thing, because it's very complicated. And then how to run it, you know, how to manipulate it, how to configure the queues, how to configure the matchmaking values, how to operate the customer service side of it, how to do all of those things. We set out 3 broad sets of like high-level goals. Goal number 1 was given the CAP theorem, which is kind of consistency, availability, and partitionability, you can pick two. And whichever two you pick, the other one is not going to work very well. For a game, you don't need 100% consistency all the time. It's not a bank, it's not a financial system, but you probably want your availability to be as close to that as possible. Otherwise, people are going to get really upset and not play your game, especially if it's a free-to-play game. We wanted it to be good. Obviously, different areas of the business define good differently. We wanted it to be fast, i.e. react to player behavior or low latency, depending on who they're playing with. And we wanted it to be cheap, right? So we didn't want to spend loads of money on hardware that we don't know if we're going to use. At the same time, we didn't want to spend loads of money on staff to have to manage the thing once it's in production. And I think that second bit, the people that you have in your team are way more expensive than any investment you could make in a piece of software or a piece of tech. And I think far too many teams just think, oh, the balance sheet, the bill for that thing is too high. And they don't think, actually, I'm going to need 3 more people to be able to make that work. It also needs to be powerful, flexible, and easy, right? So like I say, this game was going to be very rich, very complicated. We didn't really know. Potentially, we'd want to take this whole set of stuff and build a completely different game. Maybe it wouldn't be a total war game. Maybe it wouldn't be free-to-play. Maybe it wouldn't be 10v10, which is where we ended up. Maybe it would be a 1v1 mobile card game, which was exactly where we ended up, right? We built a mobile card game using this stuff. Problem, again, needs to be powerful because we don't know quite, which way we're going to know. It needs to be flexible so that game designers can change their minds because they like doing that. And we need to be able to keep up. And it needs to be easy to use. So the people building this stuff were people like me, who are engineers who have spent their life configuring things. They muck about with config files, spend their life in /etc. And then you give that to a game designer and say, hey, I've built you an abstraction of an inventory system. And you can model any hierarchy of any type of item, and you can define any validation rules of any complex tree of who can be attached to what and how many and everything else. And they say, does it support currency? Well, yeah, it does support, and it's an item, and it can go anywhere in tree. Does it support swords? Well, yeah, that's an item too. And suddenly we realized that actually this thing that we've built, it's a really nice abstraction, and you can build all the games. But now you need to help the game teams understand how they can sort of capitalize on that power. So for each of these 3, we kind of ended up with, let's aim for 2.5 of each of them. The stuff AWS provides, you can't have fully consistent, fully available, and fully partitionable. But things like S3, things like Dynamo, let you get pretty close. And if you're willing to make some sacrifices on things like consistency, it's a game. It doesn't mean you have to be inconsistent. It just means not absolutely inconsistent, right? And there is an enormous difference between nearly and absolutely. Good, fast, and cheap. Well, we'll aim for cheap-ish, and we'll aim for good-ish, but it does need to be fast. That one is non-negotiable. Powerful, flexible, and easy. Easy for us, which meant we need to work really closely with the game teams to help them understand how. We were building this, like I say, from 2011. The cloudscape at the time wasn't very mature. There wasn't a whole load of stuff available. And some of the services that were coming out were really, really game-changing. Things like DynamoDB was like extraordinary. You click a button, you have a database, you can save things into it, and you can pull them out again. You don't have to think about it anymore. But it's eventually consistent. That's annoying. You now need to write a whole bunch of code around whatever it is that you're engineering using DynamoDB to handle the eventual consistency. Okay, fine. It's engineering work, whatever. It doesn't scale itself. You kind of have to tell it, I want this many IOPS, and I want that many read operations, I want that many write operations. And then you can scale it down a few hours later or a day later, but you can't do it too many times in 24 hours. So, that's annoying. All right, let's write some software, and we'll watch the queues, we'll watch the number of users online, we'll try and predict, and then we'll scale up and scale down. All right, fine. So we're running a bunch of EC2s to try and scale our Dynamo. And then pop. Amazon announced a thing. They've just released fully consistent writes for Dynamo. They've just released automatic backups for Dynamo. You tick the button and it works. They've just announced on-demand scaling for Dynamo. And suddenly, Dynamo really is this wonder bread. that you put things into it, you can get them out, and they're consistent. You write 1 million items a second or 5 items a second, and it will scale to handle that. You want backups, and you tick the backup button, and then you go back to sleep. Backups, same deal. We'd write a bunch of stuff in Jenkins with Bash, probably, because we like Bash. We'd evolve that, make it bigger, make it better, make it more production-y, and make it EMR and S3 and all sorts of other stuff with cross-region replication and blah, blah, blah. And then Amazon would say, oh, by the way, we just released full cross-region replication with a tick box on whatever service it is you happen to be using. And that pattern kept happening. We'd invest a bunch of time and energy trying to solve a problem that we had in production now. And then a year later, there'll be a fully managed one, which means we can throw all of that code away. We don't have to maintain it anymore. We don't need to keep upgrading the test cases. We don't have to maintain any of it, and we can go back to sleep. So turn on the AWS managed one, carry on with your life. We saw this on EC2 for spinning up instances, hibernating them, making them go back to sleep, orchestration stuff. We wrote a bunch of things around there. Having event-based programming based on S3 events, same thing. We had this for Kinesis and Lambdas. We thought, wouldn't it be wonderful if there was a managed version of Kafka that we don't have to think about. We just want to pull events out of it and fan them out to, oh, look, there's one, Kinesis. And it works with Lambda, and you don't have to think about it anymore. That's kind of our journey, right? Start at the beginning, write a bunch of code, and by the time you get to the end, you're just ticking a bunch of boxes of which features you want enabled in your box of Duplo that you're using to build something really cool. At this point, fast forward a few years, we've got a bunch of games, we've got a bunch of tech, we've got a bunch of APIs, we've got a platform. It exists. Users sign into it, they authenticate themselves through whatever platform they happen to be playing your game on. And there's a whole load of features in use across a whole load of games. All of the APIs on all of the services that we've released have to be backwards compatible. I can go into my loft and dig out the box that's got the Xbox 360 in it. I'd have to do some rummaging, probably. Find Forza, put Forza in my Xbox 360, message my brother and get him to do the same thing. We'll both say matchmake, and we will end up racing against each other now, today. And the fact that that game was released absolutely ages ago, and all those services and everything else still works now, is exactly where we want to be with everything that we're building 10 years ago and in 10 years' time. The games that we're making, they're designed to be long, live service games. They're not designed to be ship it and forget it, right? Which means our service, our platform, our APIs, and everything that goes with it need to be able to do the same. We've ended up with 56 Amazon services in use. So that's everything from EC2 all the way to Kinesis and Athena and everything in between. Haven't quite figured out how to use ground control. That's the one that lets you manipulate satellites, but one day. And we've got that running across more than 30 Amazon accounts. There's an awful lot of infrastructure. We've got games that are running on Steam. We've got games that are running on Epic, which is another Steam-like, in case you're not aware. And we've got games running on the Microsoft Store, the Xbox for PC. We've got some that are running on all three. We've got some that have cross-play across all of those things. We've got some coming on console. We've got some already on console. Well, Hyenas is a first-person shooter on console. Once you've got all these games, all these different APIs, all this different stuff, and we've built up a bunch of processes along the years of how to automate it all. You can't automate it unless you've authenticated yourself with it. So your CI needs to be able to manipulate your infrastructure, whether it's in one account or 30. Your people, your developers, your engineers, need to be able to tinker with stuff in development. They need to be able to try out new services. They need to be able to interact with the customer support tools. They need to be able to configure the game in the game management tooling. And you need to be able to authenticate that they're allowed to do the thing that they're trying to do, or that who they say they are. Years ago, someone told me there's a difference between authentication and authorization, and I can never remember which. So those two things have to happen at some point. You've also got servers in AWS. You've got servers internally running your CI. Maybe you've got cloud CI, and they need to do stuff with servers. So your servers need to authenticate with each other. Sometimes they're in AWS, sometimes they might not be. We've got dedicated servers running in random data centers in Russia. Your services need to be able to authenticate with each other. They're sending service calls. Maybe they're sending calls to the dedicated servers to spin up another box ready for another battle. Maybe the battle server needs to be able to send back a message to service saying, hey, these people just did this thing, and this is the outcome of the battle. Again, some of this is in AWS, some of it's out. If everything's in AWS, use IAM and go back to sleep. If you've got some stuff that's not, then now you need to think differently. So where we've ended up is we've got IAM, the AWS Identity Account Management, to authenticate all the AWS things with other AWS things. That works, that's fine. For our people, the players who are playing our games, sometimes we want them to interact directly with the AWS services, things like Kinesis, things like S3. And if they can pull stuff directly from S3 without any of our services needing to get in the way, that means we can sleep more and Amazon have to deal with it. So if we can authenticate our players with IAM, basically, that's even better. So that's what we've done. We've created the CA account, which is an authentication service that we built, that authenticates a user on behalf of us using STS, which are the session tokens, as part of IAM, to grant temporary credentials to that user for that session to do certain things on certain bits of AWS. Means we have less stuff to manage, less servers that we need to configure. Our people sign into Azure Active Directory because we've got Microsoft everything in the company, and we use the Azure single sign-on, pair that with AWS single sign-on. So all our people sign into AWS via the normal Microsoft directory sign-in stuff. And then we've hooked that up into HashiCorp Vault. So when we've got service keys, things that CI needs to be able to do, that not everyone in the business needs to do, you can authenticate with Vault. Vault will give you some keys that will let you do something for a while, and then you can be on your way. Aside from authenticating, you need to be able to build it. You need to be able to test it, and you need to be able to deploy it. And you need to be able to do that with 56 different AWS services in use, and you need to do that across 30 accounts. You probably need to do that with 40 people in your team. Then you need to be able to monitor it, and you need to be able to run it. And all of this stuff is really, really not easy. Basically, if you don't automate it, you're just creating pain for yourself later. So we automate everything. Like, as a kind of guiding principle, we automate everything. And it doesn't have to be super duper, mega wonderful, awesome automation from the beginning. So we start with bash usually, because why not? You're trying something out, you want to fiddle with it, you're using the AWS CLI, and you fire up some infrastructure and it works. And you're like, well, I can't test this. I can't really distribute this. People can't contribute it. I can't refactor it and maintain it. All right, probably we need to refactor this. And our journey through IAC was roughly a bunch of bash scripts. Well, all right, CloudFormation is a thing. Let's use that. Let's build loads of big JSON templates to define our infrastructure for us. Oh my God, we've got so many templates, so many things in CloudFormation that our list of stuff in JSON is now bigger than the maximum allowed for a single CloudFormation template. And at the time, there wasn't really anything you could do about that. So we wrapped the whole thing in Python, spat out lots of different AWS templates, and then used bash to deploy them all. And that was fine, but then we realized that actually we've got a bunch of microservices, and they're all pretty much the same. And there's no point in having giant copy-pasted things. Don't repeat yourself. Everyone knows that. So wouldn't it be great if there's templates in CloudFormation? But CloudFormation at the time didn't have templates. So we used Ginger, which is a templating library for Python. So we had bash calling some Python that funneled through some Ginger stuff to pipe out CloudFormation templates in various configurations and values. And then we'd deploy the whole thing with bash. And that got untenable. So we thought, you know what will make this complicated system much simpler is if we wrap it in a really complicated infrastructure management system. So we ended up with bash calling Ansible, which runs some Python, injects some Ginger templates, then does the CloudFormation stuff, and then runs the whole thing with Ansible. Funnily enough, that's not very maintainable, and it's really difficult to manage when you've got 40 people trying to change it all at the same time. So we evaluated loads of different options here. We looked at things like CDK. We looked at things like, oh my goodness, Puppet and Chef and Ansible, obviously. We thought about writing our own, and then we settled on Terraform, HashiCorp Terraform. Terraform is or HashiCorp, I think, is a first-class partner of AWS. So when AWS make a new thing, they give you Terraform templates. So now we just use, or Terraform modules. So now we use Terraform to basically IAC all the things. It didn't used to be called IAC, it used to be called scripts, but someone decided that wasn't cool enough. Similar thing for observability, right? We wanted to graph all the things. We've been graphing stuff for years, and we'd settled on Graphite because it was great. It's really difficult to scale, especially if you've got 30 accounts, and each account's got 3 lots of Graphite, and each lot of Graphite needs to be scaled independently, and you've got tens of thousands of metrics being graphed all the time. What could we do? You know, how could we keep using Graphite? Obviously, we instrumented absolutely loads. We didn't want to throw that all away. We didn't want to rewrite the whole thing. So we started looking, maybe we can keep Graphite as the layer that is what the services emit, and Graphite is the layer that the dashboards query, but we can just replace all the stuff underneath. So we did. We replaced it with InfluxDB and Telegraph, and it pretends to be Graphite, and no one's any the wiser, but actually it runs way better, and it scales a lot better. It's still not easy to scale, especially when you've got so many. And Prometheus is starting to gain momentum. So we're looking at moving some of our workloads to Prometheus. And because there is a managed one, we took the, yes, Amazon, we'll take your managed service for Prometheus. So we can sleep more and focus on the difficult bits that Amazon won't do. Another component of observability is called logs. Well, yeah, observability used to be graphing and logging. Now it's got a fancy name and it's 3 things. But logging, we use CloudWatch logs for everything. Basically, every service that's running in AWS, every service that's running not on AWS, we funnel all the logs off to CloudWatch logs using a daemon, and then they appear in the AWS console under CloudWatch, and we can query them, and we can look at them. And with insights, CloudWatch logs insights, you can now go and query them all. And you can write complex queries, and you can do graphs, and you can set alerts. And when I wrote this slide, that was really difficult across 30 accounts. But apparently yesterday, Amazon, like I've been talking about, have released a tick box, so you can now do that across all your accounts. So we're probably going to re-engineer some stuff. Then we've got tracing, distributed tracing. There's things like AWS X-Ray. There's things like Grafana Tempo. There's a whole bunch of others. We haven't got there yet. It's on our list. One day we'll get to it. The whole point of this slide, this whole presentation, I hope, is that you don't start where you want to end up, but you have a vague idea where you do want to end up, and that's automate the hell out of everything. To be able to automate things, you need to know what's going on. Tracing will help us, right? We know that. We just haven't got to it. So where are we? We have a lot of Erlang in a lot of Amazon accounts. We have a lot of Python in a lot of Amazon accounts. We've got more and more things going serverless. We've got more and more things with like Node.js. We've got things running in containers. We've got things running in Elastic Beanstalk or EC2 or ECS or Fargate or whatever. Erlang is very difficult to scale. It's a fully connected cluster. It's a fully stateful cluster. It's got some really, really nice, I don't know what the word is, properties for building systems that let you sleep more. But it's difficult to scale. Things like Python running in a Lambda are really easy to scale because you don't have to think about it. You tick the Amazon scale it for me, please. I will give you my card. And they handle it. So we're trying to move bits of our infrastructure out of Erlang into things like Lambda. And because we've got ALBs or ELBs at the front, and we're doing everything by host-based or now path-based routing, we can just pick individual endpoints that are all backwards compatible and they're all versioned. We say, this endpoint doesn't need to be an Erlang anymore. Let's stick it in a Lambda and stop thinking about it, which then drops the utilization of your Erlang stuff, means you can sleep more. Because we've got so many accounts, because we've got so much stuff, we've gone all in on AWS. We kind of did that right at the beginning. There's 2 ways you can do cloud things. You can do vendor agnostic, or you can do all in on one vendor. I think it doesn't really matter which vendor you choose. I think we chose the right one. But just pick one. The whole point of cloud is that they're going to do all the complicated rubbish that you don't want to be dealing with. So yeah, we went absolutely all in. We are very much tied to all of the AWS services, but there is so much that we don't have to think about because of doing that. We've got things like AWS Enterprise Support, which gives me access to some extremely valuable resources, like Mark, among others. Right? I've never worked with any other provider, customer, solution, anything else that are so aggressively trying to make us spend less money all the time. They encourage us to do cost saving. They encourage us to do savings plans. They're trying to find other ways that they can reduce our bill. And all we need to do is put the engineering effort in to do it. We do all this stuff in lots of accounts, lots of Erlang, lots of complexity, lots of game teams, lots of all sorts, for millions of players. We have millions and millions of players playing the games all the time, and thousands of requests a second across our estate. And it's been an absolute evolution to get to this point, and I hope it will carry on being an evolution as we carry on for the next N years. Yeah. The character on the right is a guy called Cow Cow. He's from one of the Total War games. He had a lot of wisdom. One of his favorites was, failure teaches us how to succeed. And that is something we do really, really well. We fail so hard that I think we must be doing it right by now. Quick diagram of kind of where we're at. This isn't so I can talk you through every component of everything, right? There's just, obviously, as I'm sure you can guess, a lot of it. That's a high-level summary. So on the left-hand side, we've got these services, right? These are all the bits that make the game work. And on the right-hand side, you've got the platform stuff. So these are the things that are shared across all the different games. Things like authentication, things like CRM, CDP. On the left-hand side, you've got all the things like matchmaking and leaderboards and profile and inventory and balance and missions and chat, and it goes on. To do this, we found a bunch of patterns that work really, really well. One, make sure you've got a very, very well-defined ingress layer. It needs to be able to do things like host-based, path-based, or something else-based routing, right? You need to be able to configure that stuff at runtime, because at some point you're going to have a problem in one of your systems, and it's completely on fire, and being able to just dead letter the whole thing is really, really valuable. So we put ALBs as our host-based, path-based routing thing. You can switch out endpoints very easily at runtime, or you can just redeploy a Terraform thing and it will reconfigure itself. We stick CloudFront in front of that as our CDN. That makes sure that wherever the players are, they're hitting an endpoint that gets into AWS really quickly and then uses all the AWS magic to get back to wherever we're running the services, which for us is EU West 1, basically for everything. Aside from that, we use the Amazon API gateway, which gives us a really nice way of authenticating services that we use internally against an authentication provider, and we don't have to write any of that authentication logic. You can also give it an open API spec, which all of our services emit an open API spec. You can give that to to API gateway, and it will just build all the endpoints for you that you can then go in and fiddle with. On the left-hand side, we've got persistence. So these are all the managed AWS things that we use, things like DynamoDB, buckets, Kinesis, S3 buckets and Kinesis, and then RDS. So we use Postgres quite a lot in RDS. From the back of the persistence, generally we'll have some kind of event-based something. So an event will be written into a Kinesis queue, an object will be written into an S3 bucket, an item will be written in Dynamo, and that will fire a Lambda that does something. It might be that it just fires another Lambda somewhere else, or it might be that it fans it out to a bunch of services, or it injects it into some other queue. But the point here is that we've got a bunch of events happening at a bunch of different times, written in a bunch of different languages, and that's kind of all asynchronous but event-based programming. We've then got the application layer, which again, some of that is Lambda, some of it is fully distributed connected clusters of Erlang. Some of it is EC2 running Python, or anything in between. We've also got eJabberD, which is a XMPP service, again running in a big cluster of EC2 stuff. And all of those things are hooked up to things like AWS or Amazon Managed Service for Prometheus and Graphite, well, Influx and Telegraph that pretend to be Graphite. Separate from that, we've got all the regions. So when you've got a service, you've got, like I say, 2 players on the east coast of America, you probably want a relay server, a dedicated server, or something near them. So we spin up loads of dedicated servers all over the place. Some of them are C++, some of them are C#, and then we have Graphite as well to go with it. We've got 33 of those for all the different games and all the different environments that we've got running around the world. Things like the development environment, the stable environment, the QA acceptance environment, the staging environment, and then the production environment for a given game. Some games have more, some games have less. And the whole point is it doesn't really matter. We just rerun a Terraform thing and up it comes. Configure it, and then off you go. Basically, same pattern for all of the shared services. So nothing hugely noteworthy in there. But then the bottom bit. So CloudFormation, we still have a lot of it. We're moving things to Terraform. We haven't finished. Route 53 for DNS. If there's a domain name involved, it's on Route 53. That's a given for us. IAM on everything. Only permissions to access and manipulate the services that you really need from whatever infrastructure you're running. Alarms, logs, and insights. Right? CloudWatch logs is magic, and we use it for everything. We looked at things like ELK, the ELK stack, and actually CloudWatch just does it in a way that we don't have to think about it anymore, which means we can sleep more. Enterprise support, as I mentioned, really, really valuable. And the turnaround time on incidents, if you do happen to run into them, is really, really worth the money there. And then Transit Gateway, we're starting to move more of our infrastructure into private VPCs, or VPCs with private subnets, which is only accessible from our on-premise Office stuff, and then we use Transit Gateway to handle that private connection between two. So a bit of a whistle-stop tour there, but hopefully it gives you an idea that there's lots of pieces to what we've built. So what's next? Well, more games. We've been making games for a really long time. I've been at CA making games for 11 years, and I hope 11 more years. We are looking at things like multi-tenancy. Maybe we can get rid of 33 environments and just have more games in one place. It brings a whole load of other challenges. All of our graphs are built around the idea that they live in their own little world. So all of the querying, all of the endpoints, all of the nodes in those graph queries just don't need to think about what game am I, what platform am I. It's the fact that it's in that environment that defines all those things. So if we're going to start running more stuff, we need to really rejig some stuff. How are we going to make our platform easier to use for the game teams? How are we going to make it easier to integrate? How are we going to make it more comprehensible for them to configure and make it do what they want it to do instead of how we think it should run? How are we going to make it more efficient? How are we going to spend less money, make more efficient use of things like EC2, or move workloads to containers so that we don't have to manage them anymore? How can we make the game teams self-sufficient? Right now, we've got a service team who build infrastructure, and when a game needs a feature, we figure out how can we put that into our platform to make that available for all the other games. Sometimes games have workloads that aren't shared. They're super specific to a game team. But how can we let them do that in cloud, in public infrastructure, without creating another service team? Well, things like Lambda paired with DynamoDB, paired with managed Prometheus, paired with CloudWatch. Actually, you've got a really, really solid stack there that game teams can write things in C#, and they don't need to know a whole load of cloud stuff. We can maybe write a document on all the mistakes that we've made for 11, 20 years doing it. Don't make these mistakes and use these services so that you can sleep. Takeaways from my non-stop rambling. Amazon say you shouldn't do the undifferentiated heavy lifting. Personally, I've never really understood what the hell that means. The guiding principle of sleep more has let us make some really, really great engineering decisions, some architectural design principles. I think what Amazon mean is let them do the boring stuff. Right? We don't want to do that. Let them do it. They're really good at it. You focus on doing what you do. Keep in the back of the mind that you want to sleep more and figure out how you can leverage all the AWS wizardry to let you do that. Thank you very much for listening.
Thank you, Seb.
You're welcome. Thank you, Mark.
Thank you, Seb. We like doing the boring stuff. We live and love to do the boring stuff. So yeah, boring stuff, send it our way, please.
Yeah, exactly. Absolutely.
But Seb, thank you very much.
Thank you for having me. Thank you, Mark.